Hi, this is Wissner-Gross, and right now we're going to discuss carbon bond angles. So in the middle you can see carbon represented by the letter C and the four hydrogens around it. The hydrogen on the right, the H on the right, is connected to the carbon by a dashed line indicating that the hydrogen is actually behind the carbon. Remember, we're trying to convey a 3D geometry on this 2D slide. Okay, so the four hydrogens in methane, or actually the electrons that make up the bonds to those hydrogens, repel each other to form an overall tetrahedral shape. This is called sp3 hybridization. This is part of valence shell electron pair repulsion theory. We'll get to that a little bit later. So the question we can ask, an interesting question, is what is the bond angle between the hydrogens and the carbon, or the HCH bond angle? And let me show you what. So I've highlighted two of the hydrogens and one of the carbon. These are 3 points, and together you can see that they form an angle between them. So what is this angle? How can we figure that out? Well, we start out with chemistry. This is a chemical question. What's the bond angle in a molecule? But really it's just math. We can draw a tetrahedron and work out what that angle is. Now your initial guess might be 120 degrees. A lot of people think that. But that's actually not the right answer. So here I've redrawn a tetrahedron, and the center of this tetrahedron would represent the carbon, and the four vertices would represent the hydrogens. And I've indicated by the letter X here that HCH bond angle. So in green now I'm highlighting a specific triangle. Notice that it's isosceles because the two CH bond lengths, the two shorter sides of this triangle, are equal in length. So this triangle is isosceles. So that means that the other two angles, which we'll call y here, must be equal. Now the sum of the angles in a triangle must add up to 180 degrees. So x plus 2y must equal 180 degrees, or if we flip things around, x is just 180 minus 2y. And I've done this because y is actually easier to determine mathematically, and once we know y, we just plug it right into this formula, and then we know x. So let's try to figure out what y can be. So first I'm going to extend one of those bonds down to the bottom plane of the tetrahedron. And pretty soon we're going to focus exclusively on this bottom triangle, the bottom face of the tetrahedron. Now furthermore, let's suppose that the side length, or edge length of this tetrahedron, all the edges have length A. And also let's call this bottom edge of this green triangle, this green right triangle, let's call that B. So we're going to try to figure out what this angle y is in terms of A and B. Okay, now we're looking exclusively at that bottom triangle, the bottom face of the tetrahedron. It's an equilateral triangle. It has 3 sides, all of length A, and I've drawn in green here that side B, that edge B that we were talking about just a minute ago. Now we're going to look at this green triangle for a moment. Now look at the top right vertex of this green triangle and note that it's in the middle of that equilateral triangle because that is we extended the top bond, this top CH bond, down to the bottom face of the tetrahedron. So it's going to be right smack in the middle of this orange triangle. And that means a couple of things. It means that the bottom edge of this green triangle has length A over 2. And also notice that this is a 30, 60, 90 right triangle because that top left, the hypotenuse of this green right triangle, bisects one of the angles, one of the 3 angles of this orange triangle. And it's an equilateral triangle. All its angles are 60 degrees. So that means that this leftmost angle of the green triangle must be 30 degrees. And now we have a pretty simple relation between A and B, because look at this. The cosine of that left angle, of the 30-degree angle, and remember cosine is the adjacent side of our triangle over the hypotenuse, and we already know the adjacent and hypotenuse sides. The adjacent side has length A over 2, the hypotenuse is B, so A over 2 over B, or A over 2B, must be equal to the cosine of 30 degrees. And if you remember your trigonometry, which you can review in another lecture, the cosine of 30 degrees is just the square root of 3 over 2. So I've drawn that here. Square root of 3 over 2 is now equal to A over 2B, and we can find B in terms of A. B is just A over the square root of 3. So now let's go back to our earlier slide, a drawing of the tetrahedron, and now we can plug in the value for B. Now we try to find y just in terms of A. Well, the sine of y is the opposite over the hypotenuse. So in this case, the opposite is a over the square root of 3. The hypotenuse is a. So the sine of y is just a over a root 3, or 1 over the square root of 3. Which means we know y. Y must be the inverse sine of 1 over the square root of 3, or the arc sine of 1 over the square root of 3. And if we know y, remember we know x, and x was that bond angle, that HCH bond angle. So we said x was 180 minus 2 times y. Plug in that value for y. So that means x must be equal to 180 minus 2 times the arc sine of 1 over the square root of 3. And this is just numbers at this point. We can evaluate this. Plug it into your calculator, see what you get. X, the bond angle in methane, is 109.4712 ... degrees, or approximately 109.5 degrees. That's an approximation you'll typically learn in the chemistry classroom. And another way to write this, the expression above is just 180 minus the arc cosine of 1 over 3. I'll let you work that out for yourself of why that's true. Okay, let's take this last slide to just look at a couple of other molecules and see if we can get a better idea of what's going on here. So in the methane molecule, we said that this was just a regular tetrahedron, carbon, 4 hydrogens, a very symmetric molecule, forms a tetrahedron, and we measured the bond angle. We calculated it just mathematically, no real chemistry here, to 109.5 degrees. Now what about ammonia? Ammonia is nitrogen and 3 hydrogens, NH3. So the nitrogen has an extra pair of electrons that is not bound to any hydrogen. And now this lone pair, according to valence shell electron pair repulsion theory, or VSEPR theory for short, which you can learn about in another lecture, states that lone pairs occupy more space around the central atom than any of the bonds. So the lone pair of electrons kind of squeezes those 3 NH bonds closer together, so their angles will be less than 109.5 degrees, slightly. Experimentally, that bond angle is measured to 107 degrees, and you can measure these bond angles experimentally either using spectroscopic techniques or diffraction techniques. But experimentally, that's found to be 107 degrees. We couldn't have predicted that, or it would have been very tough to predict it. But experimentally, it's found to be 107 degrees. And in water has 2 lone pairs. So those 2 lone pairs of electrons are. In water, the bond angle is found to be 104.5 degrees. And if you want to remember these off the top of your head, an easy way is, well, we knew methane was 109.5 because we could derive that mathematically. And then for every additional lone pair, at least in this sequence, we subtract about 2.5 degrees. So this is all part of valence shell electron pair repulsion, or VSEPR theory, and I encourage you to look up this topic if you're interested in learning about it further. Thanks for listening.